For the next couple of lectures, we'll be looking at gases. And we'll start with this first one, about pressure. I'm assuming you know a little bit about pressure, because you might have heard it on the news about, like, say, air pressure, or, I don't know, maybe when you learned about lungs, you talked about this. But in the physical sense, we want to give a very clear definition. The pressure is defined as a force exerted per unit area. So, in math form, it's written like this. That's pressure divided by the force applied over area. Now, you see over here that the force applied has to be the force that's perpendicular to the surface on which the force is applied. I'm going to illustrate this with an example. Off we go. Over here you see we have what's called a piston, and we'll be looking at this a lot more later on. A piston is simply a container of gas that has something plugged onto one end within a handle. Alright, first let's fill a container with gas. Now we're going to push this piston inwards by applying a force onto it. Let's just say a force of 5 newtons in that direction. And you know the piston's going to go and go until a certain point where it will stop moving. And at this point where it reaches equilibrium is where the pressure exerted by the gas over here is equal to the pressure exerted outside. And you notice here with just that 5 newtons we've pushed it by so much, we've compressed the gas by so much. That means, well, we've applied quite a great amount of pressure here, right? Now, let's change the scenario up a bit. So we apply the same 5 newtons, but this time we apply it at an angle. If you look at the force component the component of the force vector that's in the perpendicular to the surface, which is now this, we're really applying this little bit of force over here, which we'll say is 4 newtons. And so as you'd expect, because we're applying a less amount of force that is giving us a change in pressure, our pressure is not going to increase by that much. We might go, oh, push, and then we'll stop here. So in this case, at the point of equilibrium, we find that we haven't compressed the gas as much as before. A very simple illustration. Hope it helps somehow. Now, let's illustrate the effect of changing area on pressure, and this time with a more concrete example. Let's say I had a penguin, and I had a hammer, right? And I'm gonna use this hammer to slam on the penguin. Actually, no, that's too violent. Scratch that. Instead, let's have a box. Okay, that's a little friendlier, PG-13. And we're trying to use this hammer to hit the box. We're trying to break its outer barrier, and we're not doing very well. We can't penetrate it. And you know that if you put a nail over here, so if we hit the nail, bing, that nail is going to drive its way into the box. And how the nail works really gives us a very good idea of this relationship that we see over here. Because essentially the nail reduces the area that the force that we applied on the hammer is going to exert over. So if you reduce this variable over here, we have the denominator decreasing, now we have pressure increasing. So we've exerted a greater amount of pressure with the same amount of force. On to my next point about pressure. Now, lay people untrained in the arts of physics tend to misuse terms. They say stuff like, I'm applying pressure in the downward direction and stuff like that, But pressure is actually a scalar quantity. It means it has no direction at all. Let me illustrate this with this guy over here. It's our magical balloon. It's invincible. It can't break. It's like the Hulk's pants. So within this balloon, you have lots of gas particles. And each of these is bouncing around and hitting against the walls of the balloon. And every time it hits against a side of the balloon, it exerts a force, right? For example, this one over here is going to exert a force in this direction. So over here is going to exert a force in this direction, in this direction, like that. So forces exerted on a micro level across the surface, the entire surface area of this balloon, results in something like this. So you see here we have all these micro level forces that ends up exerting a collective pressure on the balloon that keeps it inflated. And this pressure is acting in all directions. So there's no one direction in which pressure is acting. So if you think about it that way, since there's no one direction, well then pressure is a scalar quantity. And to make this picture even clearer, here's what I'm going to do. I'm going to shrink this balloon down until it is a point. Note the direction, or the so to speak direction, of where the pressure is acting. It's still going to be acting in all directions. So our invincible balloon has showed us that the pressure acting on at any point has no directionality. And we'll look at that closer when we look at an example later on. But now I'd like to take a bit of a detour and talk about the concept of a gauge pressure. Now gauge pressure is basically the pressure relative to atmospheric pressure. And mathematically I write it as this. So absolute pressure over here is just the pressure that you actually have. And you deduct from that the atmospheric pressure, which I'm just going to give it to you at standard conditions, would be 101,300 pascals. One thing about the gauge pressure that you wouldn't be able to find in the atmospheric pressure or the absolute pressure is that it can be negative. And how does that work? Well, if your absolute pressure was lower than atmospheric pressure, then well, gauge pressure would naturally just mathematically be negative, right? And when would that happen? So for example, if you are breathing in, so those are your lungs, and when you breathe in, the pressure in your lungs would decrease relative to the atmospheric pressure, and that's how, and since the pressure is lower than the atmospheric one, air is going to rush inwards, like that. Okay, that's a terrible drawing. But you get the idea of how it might be negative. Our last job of the day is to look at an example with a piston, like once again. So the question reads, to prevent a piston from moving, it's got a circular piston with an area of 5 meters squared. So this is the surface area over here. It must be pushed towards a sealed gas with a force of 10 newtons. And what is the pressure of the gas is our question. So conceptually, here's how we get it, is we're going to apply a force of 10 newtons on this handle on the surface over here, and we're going to keep pushing it until it reaches a mechanical equilibrium. So our 10 newtons cannot move it any further. So let's write down what we know. Now if I arrange those variables a little bit, we also know that force is equal to the pressure multiplied by the area. Okay, now let's draw a free body diagram. It's back. So let's say this direction is positive. Why not? So we've exerted 10 newtons on the piston, and we have the gas pushing back. Okay, so where did it go from here? Well, most students, they look at this and go like, oh look over here, 10 newtons in this direction, that's 10 newtons in that direction. Wow, that's isn't too easy. But actually, you forget one thing, and that could cost you your life. No. You forget the fact that we haven't considered atmospheric pressure. He's thinking, well, you don't have to, right? Because atmospheric pressure, think about that. The atmosphere is up there, so it's pushing down like this, so we're should be basically immune to that effect, isn't it? Well, that's not true. And here's where you have to remember what we talked about before. We said that pressure is a scalar quantity, it has no directionality. So at every point of space, I guess, in this case, that is exposed to the atmosphere, you're gonna have atmospheric pressure. So imagine many more of those points. And as long as it's touching, it exerts an effect over this area, it's gonna give rise to a force in that direction. And so we have to include that, a force that arises from atmospheric pressure. Now let's solve this free body diagram. We have mechanical equilibrium, so the forces all balance out. Now we know some values over here. We're trying to find this, and we know the area because it's 5 meters squared, right? And we also know the pressure, the atmospheric pressure, which I gave earlier as 101,300 pascals. Now all we have to do is isolate for the variable we want to find. That's the pressure of the air inside over here. And I've already done this, and the answer we have is... So you see, I haven't actually increased the pressure by much relative to atmosphere at all. Probably not a very good example. Should have used bigger numbers. But if you were an especially smart cookie, you would have realized that this extra force that we gave in, that resulted in extra pressure, is actually pressure that we added in addition to atmospheric pressure, which is also the gauge pressure, right? So hopefully you spotted that. We just learned it. Hopefully you understood that. And see you soon.